Hello everyone. So today again we return to measure theory, and this is a very interesting topic once you try to play with it in Julia or basically in any other language, but I prefer Julia because it's slightly easier to code and you can build animations using it. So I have been using a lot of Julia from time to time. But just to remind the premise, the basic premise I understand from measure theory is how it leads into probability. All of it is mapping things into a number line. So first thing I always say is that it maps it into a number line. So always you can think of it as mapping. And second, once you map, you can calculate any kind of probabilities. So then this becomes easier because then once you have mapped any event to these lines, then you probability is just measuring the length of that interval. And that's where the things like move forward and you have the whole probability space kind of terms, and that is a lot of jargon is introduced once you get past this. But initially, when anybody starts doing this measure theory, they get lost in a bunch of symbols because then the terms become way more complicated than it usually is. And I feel that this is something that it's not taught in a intuitive way. It is taught in a very symbolic way, which becomes a bit of problematic thing. And hopefully, I think people will note later. But anyway, that's a separate talk in itself. It's a very interesting topic. And honestly, whenever I look at YouTube videos on measure theory, I find it so boring that I think it's just symbols and numbers thrown here and there. So, anyway, before this becomes about symbols, I will try to move into the coding part and share what I mean, how things work. So last time, I think we were doing something like this in Julia, which was mapping any of the sequence here into this omega, which is between 0 and 1. So basically, you could map heads to this zero point 0.5 or any sequence to this number. You can revisit the previous video to check it out. So idea was that just to remind everyone that if you are, let's say, doing something like HT, then it used to map to this is 1 by 2 plus 0 by 2 to power 1 to power 2. So this used to map to zero point 0.5. And if I get HH, this will get mapped to 1 by 2 plus 1 by 4, which is equal to 0.75. So all this mapping we discussed, and that's how the Rademacher functions were born. And yeah, we tried a lot of different combinations. But returning back to the code, so let's revisit the code as I was saying. And this is pretty simple to use. And we will talk about how the things work. First example, as I was saying, is simply where you map a sequence. And as I was saying, if I do HT, it maps to zero point 0.5, HH, it maps to zero point 0.7. I can map any sequence and it will give me a number. So that is all simple, but as I said, what's the point of mapping? Why we are doing this? So let's dig down into this idea. First, as I said with Rademacher functions, simply they are alternating between +1 and -1. And just to showcase for first toss, it is +1, -1. You have two tosses, you have +1, -1, +1, -1, or sorry, -1, +1, -1, +1. So this is just mapping the number space. If I do 10, then of course this becomes a bit difficult. 20, again, the lines are like more closer, and you can keep on doing this for different combinations, right? It's very easy to check what Rademacher functions are doing. But how do I write the code? Basically, all I am saying is that x is something which is split between this values 0 to 1, and I'm dividing this interval into very fine lines, like first is 0, then 0 0.01, 0 0.02, 0 0.03, because so this is my increment. And this way, x is all these values. And I can just to showcase, I think I can print out, but I think it might print out the exact number if I do this. Right? So it will just print out this. Actually, it is not showing the exact values because that's how Julia represents the array of this fixed numbers. Okay. Anyway, now what I'm doing is initially I'm filling y with all the -1s. And then think of the simplest case when this is 1. I know that this upper limit, this is 1 and this is -1. So basically all I have to figure out is where to cut the intervals, and that's how it is doing it. Because for the first one, when I is 1, the lower limit is 0, upper limit is 0.5, and number of tosses are 2. If I change to 2, then it is 1, 2, 3, 4. 4 tosses. Similarly, 3, 8 tosses. It will keep on changing. Now that's just the mapping part. How do we make use of this function? If, for example, this is my sequence, then how do I figure out where I mean, last time I think I discussed the gambler's dream problem. It is very simple, which is just saying that, okay, how to determine when I will lose money. So basically it is something simple at, okay, I remove this print line here just to make it simpler, and then I rerun this. So toss 1, I made 1, toss 2, 0, 1, 0, 1, 0, negative. So basically the game finishes at toss 7. It is very easy to see why, right? I mean, I know the pattern. So if let's say I'm doing like something like number of tosses is 11, and this was my game. If I started with TT, then I won't even make past the first toss, right? And it is expecting 11 tosses. So let's say I make it 4 and make it HHH. So the game finishes at first toss. What about this? Game finishes at third toss because +1, -1, -1. So basically that's how the game is going, which is, I mean, it's a simple of coin tosses. But the point here is that why do all these things? It is very simple to calculate. But this helps in calculating probabilities once I map the event, right? Because if I can map this event to the number line, then all my probability calculation becomes simply measuring the length of the interval, which is the idea behind measure theory. So if I go here, let's say this is my gambler's dream problem, and I try to, last time I wrote this expression, which is only saying that any number between 0 to 1, I am mapping, because as I showed that you can map any number 0 to 1 to a set of let's say head and tail pattern. And if this is greater than -1 for total number of tosses, but for exactly for that, it is -1. So basically, when K reaches this, then you know that you lose the whole money. So how do I write this kind of code? I say that, okay, I will start with 2 tosses and then go on till maybe 10 tosses or 10 tosses, and then see for each of the toss, I calculate the Rademacher function, and then I calculate what is the set of values where the loss doesn't happen. Basically, I want to enforce the loss, no loss case before the process complete. So this measures the, basically this I am measuring the length of interval where the loss doesn't happen. And here I am measuring the length of interval where the loss does happen. Because if it is not equal to the number of tosses, I don't want the loss to happen. Here I want the loss to happen. And this x1 and y1 is coming from this Rademacher function. So you can just intersect these two sets to find this final set, and this becomes my probability. And it is a very nice animation to look at actually. If you try to visualize this animation, how does this work, then it is very interesting that how the probability is changing. Let's say, okay, number of tosses is set to this. Let's change the number of tosses to maybe 16 and then see. See, it is going from 8 to 9, and see the probability is changing this way. Now the problem with this is I can't see the values here because it is like, okay, very small values. So maybe I change the y limit to 0, 0.02, maybe that way. So see, after the sixth toss, the probability is between 0 to 2% because I made sure that the limit is this. When is the probability less than 5%? It is interesting to see. Let's try, because I made sure that the y will only appear when it is between 0 to 5. And you can see as soon as this fifth toss happens, this probability is going here. So with these things, it is very easy to kind of plot and see the values. I went till 20. Maybe if I go to 30, maybe it will crash, because remember, as soon as you go to 30, the number of tosses that you are doing is 2 power 30. So it's not easy to have so many combinations being produced each time. So that's why you see the code is taking so much time. But anyway, the purpose is to just see the animation and understand the intuition why the mapping is important. Once you map the event, you can easily calculate the probability by just assigning, or sorry, not assigning, measuring the length of that interval. So let's extend this analysis to something which is more, slightly more complicated, but still easier. Let's do this thing. Let's say this is my sequence basically, and all I'm trying to do is this. This is the series that I'm trying to visualize, and all I'm saying is that this series will converge. So what is the series R in W? This is just my Rademacher function. And for first toss, any W I can choose, and I can be sure that after some number of tosses, this will converge. And I don't want to choose W between 0 to 1 because, I mean, that will make the interpolation too complicated. So let me explain what I'm trying to say here, which is a bit easier this way. So this is how I'm trying to sum this, right? And why do I say that this series converges? So for example, for let's say W is anything, instead of a number, I'm saying it is a series of patterns H, T, H, H, T, 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 H, whatever. So I know if I do R1 W, it will be 1, R2 W will be -1, R3W will be equal to +1. So you see that you can make the series, but how can I say that the series converges? I mean, all I'm doing is 1 by 2 plus 1 by 4 plus, sorry, this is -1 plus 1 by 8, and different terms depending on this. The claim is that no matter what pattern you choose, this series will converge. And let's check it out first in code, how it works. So what I do is I'd written some code assuming this sequence. I can assume any sequence, but uh, here what I've done is I've coded this Rademacher function a bit differently. That whenever instead of mapping from 0 to 1, all I've done is if it is H, is 1. If it is tails, it is 0. Sorry, it is -1. So this gets mapped here, and then all I do is I plot this. So you can see that this looks like it is converging, but I still cannot be sure because I don't know whether it is going from 0 to 0.01 to 0.02. Let's see in the animation. And here what I will do is I will restrict the y from 0.05 to 0.5, and I will just plot this sequence. What is the sequence? Sequence is nothing but this, and it will map this to simply the Rademacher function, and then I will check whether my plot, how it changes. Let's just see the plot first and keep the animation speed at 5, so should be fine, I guess. Better to do it this way. Okay, so see why it is going up, because all the values are greater than 0.5. Now you see it is going down, converging. Looks like it is converging, but still cannot be sure. But you see that the values are now within the range of plus zero point 0.5 to minus zero point 0.5, and it is still going lower and lower. And it has reached till 150 and it is going down. So there's a mathematical way or a rigorous way to say this is convergent. But initially, I believe that rather than the symbols, it is important to see visually what does the convergent terms mean. How to express this in a rigorous way, there's a mathematical language for that. And it is really beautiful if you look at it and if you learn it. Because if you look at that statement and you can visualize how the graph is moving, it's like understanding math at the deepest level. And this theory works for any example. in finance. So let me just change the limit slightly more just to have a bit more fun. And let's see this with limits change from -1 to +1. So you see it takes a bit of time to code because, yeah, it takes a bit of time to run. So now the limit is even smaller. And let's see, can even hide the code here. This was the expression, very easy to write in LaTeX. And see, till 100 even it is not converging, but and that's the language you have to express. I mean, once initially when mathematicians started this, I mean, the theory of converging series, then somebody might have looked at this pattern and then decided how to write this rigorously. But what we do in classes, we read the expression, we memorize it, and we forget it without realizing that, okay, why this is working. You see, it looks like converging, right? You can visually see it very beautifully that it is coming within this range of minus zero point zero 0.05 to plus zero point zero 0.05. And see this whole animation going from here to here. And you can even go lower than that. And if you try to read the definition of this convergent series, it will be about a small ball covering this region so that even if you squeeze the ball or if you cover the area, it will cover this point and inside, outside. A lot of rigorous definition is there. But I think I can explain that definition also, but I think I prefer to do it visually first. So hopefully this makes sense. It's a very interesting subject. And if you are into finance quants, then this understanding is very, very important for doing any kind of trading or any kind of analysis on the stock prices. Because what you are learning in stochastic calculus, it's just already been done in measure theory. It's just taken out of it. It's just a different name, I will say.